Middle Egyptian grammar. So we're going to start with 12th dynasty. You've all read to chapter 9 in the textbooks, I hope. This is where we're going to start. No, actually, this is the name of my company is Sobek Media, and that is the Egyptian god Sobek. And this is actually just means starting soon. Let's not skip ahead too quick. So my name's David, Davo, Dave, or Lucky Jack. Any of those is appropriate. I've been called all of those and quite a lot worse over the years. I've led a reasonably diverse life. I've done actual genuine science at the Cavendish laboratory in Cambridge, and I've swept the floor at a warehouse in Droitwich. So I don't mean to tell you which one of those two is the more fulfilling. I really love that dustpan and brush. Friendlier people. So there we go. That's me. So that's working really well. But anyway, so a little bit about myself. So I'm principally a programmer. And so we'll just have a little bit of a timeline of me. So this is CPC 464 code. You'll be able to see there, that's a Z80 processor. That's the processor that ran that in the 1980s. We go on to C. Anybody remember Turbo C? Actually was quick, and it has the name Turbo in the title, so can't be bad. Turbo C++ is completely different. Then, for my sins, move on to x86 assembly language. So connoisseurs among you might notice, see the dots not showing up very well here. But the MMX registers, they were a joy. And how many people forgot that little line of code there, which basically just corrupted everything else you tried to do, because MMX is an instruction set, but it was a hack. And just basically left junk in your registers. Java, which is step up, step down, step sideways, who knows. PHP, again. And latterly, for us who work in data science or pretend to work in data science, that's shader code, which runs on GPUs. And actually, if you use it for proper applications as opposed to games, you're not supposed to call it shader code, but I don't know what else to call it really. Educational background, we start with biology. Again, for the connoisseurs. I photoshopped the cat into that picture there to illustrative of biology. But this isn't the type of biology I did. I actually did bachelor biology. Put the cat in again. Just kind of like the cat. But my principal university work was dealing with my molecular biology. So this isn't a particularly wonderful diagram, but mainly transport across cellular walls was the kind of thing that first got me into big data. So moving different nutrients and different chemicals and ions across cell walls and experiments. And we're talking back in the relatively early days of hacking. If you wanted to do parallel processing in those days, you literally cut a hole in the case and solder things onto the motherboard. And it's interesting. One rule about cutting holes in computer cases and soldering motherboards is, do it to other people's computers, not your own. The next step in big data is we'll give you a push your hands together now. Quite hard enough to push the electrons into the protons, the molecules, and then you'd get what's known as neutron degenerate matter. And this was another thing we did that it's clearly molecular biology. Did a project where we're actually trying to find whether there was an intermediate point between a neutron star. Should have put a cat in this really. And black holes. So you can make an argument to say that neutrons are the densest objects in the universe. because black holes don't actually have a volume, so they can't have a density. But that's a semantic argument. Yeah, is there an intermediate between neutron stars and black holes? No. Although there is exotic matter theorized to be in the center of neutron stars. But anyway, skipping through the slides here. Expert with the use of slides here. So again, I mean, essentially why that move was made was because the work on molecular biology, stringing kind of computers together, very applicable for the people in the physics department. And I think the computer science department were putting digitized versions of their faces on that, you know, the character on the bottom of the Screaming Doom. I think that's what they occupied themselves with. So I was kind of next on the list to call for some computer expertise. And yeah, because I like always like to think of myself as a very narrow specialist. You know, maybe one of these days I might branch out into some different things. But latterly and kind of currently work in ancient languages. That's an example of some ancient languages, by the way. That's not graffiti. I've photographed a Foregate Street station. So it's cuneiform writing. So I won't go into it too much because you'll never stop me. But essentially, it's a what's known as an abjad script. So each of these symbols, that pointer really doesn't show up, does it? Represents a consonant and a vowel. So instead of letters like we have, you have a consonant vowel. And actually that's similar to how ancient Egyptian works as well. People think ancient Egyptian is, you know, you got a picture of an owl and it means owl. But actually an ancient Egyptian owl actually means M. And yeah, so it's kind of a bridge between logographic writing and more modern kind of alphabets. Obviously, alphabet's more universal and you have fewer symbols, but, you know, bless them, they're only starting out. So, but it does actually, I mean, if you look at this, I mean, you have to think of in terms of the Latin alphabet we use can be used to write French, German, whatever. And it's exactly the same with cuneiform, that a lot of these symbols were used for different languages. So for example, that there, which you can't see, I'm just going to point to it with paper, is Sumerian. And that is very, very complicated language. That's what's known as an agglutinative language. Yeah, good luck trying to read that. Whereas this is Old Persian. Probably take you a couple of weeks to learn that, he says. So let's move on to some computery stuff. So this is Z80 processor that we have in front of us here that's flashing lights. So I wanted to kind of start with basically how computers think, and this is at the basic level here. So I don't know how many little rascals we have in the audience that's ever done any exploitation or cracking, but this is actually a visual demonstration of what's known as a knob slide. So the lights here are the processor trying to access memory. Bless, it's not attached to any memory. But you'll see the data lines here, what it thinks it's getting back, are all pulled high through these, pulled low rather, through these resistors. So that's sending the essentially 8 zeros, which corresponds to no operation. So hence where the term knob slide comes from. But yeah, if you were to move these resistors, you know, you could get go back a little bit here. So all of these instructions here essentially correspond to just voltages on a CPU. I was actually going to wire up a Pentium. Pentium 2 used to come like in a card, so theoretically I could have wired it up, but yeah, that's 20 hours of my life I'm never going to get back. But essentially all of these instructions here, the instructions are just electrical signals going into CPU, and this Z80 from the 1980s works in exactly the same way as your modern computer does these days. There's no magic, unfortunately. I kind of wish there was really sometimes. I mean, obviously modern processors have a little bit more of a complicated architecture on the inside, but at the end of the day, it's just voltages. So go. Right, so yeah, this is one thing where I was going to, we're starting at the real early stuff here. I hope some of you will be able to see this monitor. Put your glasses on. So one of the most basic computer algorithms is pathfinding. And it's a good example of kind of just seeing a little bit of an extension of how computers think. So unfortunately, this is a very small diagram here. But yeah, if you see here, let's see if I can lift this up a little bit. It's what's known as Dijkstra's algorithm. So I've just drawn one dot there. Program that. Oh, wow, you're a genius there. And you see the grey area is where it is searched. So essentially, Dijkstra's algorithm is a bit, well, it just goes out in any direction. And then once it's found the endpoint, it can use a little bit of Pythagoras to actually find its way back to the beginning and give you the shortest path. So the next thing up in computer thinking is a little bit of heuristic. So what's known as the A-star algorithm gives you, it takes into consideration a calculation of the distance. So it knows where the end point is. It doesn't know exactly where it is. Well, it doesn't know anything, it's a computer, but and so it knows roughly what direction it wants to travel in. So if you see the area that it searches, so it's not a uniform shape there, but you see it searched a much smaller area. It's moving a pixel and then thinking, right, I'm a little bit closer, so that's okay. It's still spreading out a little bit. You see it's a much more efficient algorithm. That's a heuristic that's using there. So we can also draw little barriers on there. It's much better if I was able to show you on the screen. Click. You get what it is here. So we go for the simple algorithm again. Hopefully I've not left any holes there. So I've just drawn little little U shapes around it there just to make it a little bit more complicated. See, I'm calling it when it's a computer. See, you can understand why people get emotionally attached to AI. So again, it's Dijkstra has just kind of searched everywhere and eventually found its way there. And then,
what are you saying, David? This is the basic level of intelligence.
Smile at me. So see the mouse usage on the thigh there. And it actually is using the mouse. Trust me, I'm a professional. So right, and yeah, click use A-star. Find path, and you can see that it searched a much more efficient area. So it's kind of gone out, but still you can see where it's left the top of this U shape, but still it knows it needs to head in this direction. So that's why it's favored these kind of areas here that's heading down towards its destination. I did actually put it so you could run it in slow-mo, but I think actually we'll probably skip that bit there. But hopefully that kind of gives you the idea of all of these things, the way kind of computers think are built kind of sequentially upon one of, and nothing is magical. It is just a series of kind of logical steps. Like I say, the processor there is just working on electronics. Inside the electronics there is just capacitors, resistors reacting to it. You can tell that processor to add two numbers together. It's not adding anything together at all. It's just completing a circuit in the way that it was designed to. So, right, here we go. Let's talk about one of the big chess, computer algorithm things, chess. So there are different approaches to a chess engine, but essentially, again, modern chess engines can't play chess. A modern chess engine doesn't even know what shape a chessboard is. A modern chess engine, 64-bit computer, it's represented just by 64 noughts and ones. Some people have actually asked me whether, because you can actually just represent a chess position just as a line of 64 characters. Actually, in modern chess engines, you'll have the white pawns, white knights, white bishops, all as separate 64-bit strings, not strings, integers. And yeah, people say, oh, could a human being actually play chess just by looking at the numbers and the strings? But yeah, very good human chess players don't even need to look at the boards. But yeah, this is essentially how chess engines initially started, what's known as brute force. And brute force is really required because, is it this slide here? So yeah, perf-T just means performance test. So if you write a chess engine, you have to run it and make sure you get all of these numbers. So starting board, there are 20 moves. There are then 20 responses to each of those moves. So yeah, just going through them. Yeah, there's 20 responses, and you can see just how the numbers grow over time. Now, if you're a human being playing chess, you maybe you could do 400. You've got an hour and a half on your clock on an OTB event, so yeah, maybe you could do that. But after 3 or 4 moves, you're starting to get into real trouble. So you kind of need a heuristic. You need to choose which are the most likely moves and the best moves. But initially, chess engines would just brute force it. They would just all of the moves. And then, of course, with older hardware, you know, you're running into a limit of probably around sort of 5 or 6 move mark. But if you're looking at every single eventuality over kind of 5 or 6 moves, you're playing a reasonable game of chess there.
So that, go back one, David. So that 15 moves ahead, that's the number of different possibilities for a move.
Yeah.
Which is what? Oh, I can't even say that number, to be quite honest.
No,
I mean, even 2 moves ahead, I'd be struggling to get 4. But then with that, that's just like, say, brute force. That's just every possible move.
Every possible move, yeah.
But for a human, it would eliminate some of those. I don't know, visually perhaps before.
Yeah, so
the 400 would, yeah. Sorry,
I have a chess position here to kind of give an example. Unfortunately, Lee Chess managed to draw the arrows on there. But yeah, this is a similar number here. So there are 48 legal moves in this position. And then the 239 replies to that. But yeah, if you're a human being looking at that, you obviously have to disregard a certain number of those moves. One of the questions that does get asked is how far ahead do chess players look? And of course, it's kind of like a variable thing because you have moves like check, for example, where the opponent has to move out of check. So if you put your opponent in check, that's very, very easy to calculate. And so beginners chess courses will talk about, you look at checks, captures, and threats, because they're the most easy to calculate. They're the forcing moves. So obviously here we have an undefended bishop, which is looking pretty sweet. I'm just trying to think why that isn't the top move. Should have some thought into it. But yeah, so if you're if you're a chess player looking at this, you would you'd obviously be looking at that very tasty bishop that's been left there as a gift. But also, it's not always the most obvious move there. So I mean, it's definitely worth looking at whether because again, this is a forcing move here. If you capture the knight with the queen, it's got to be recaptured. So sometimes there are tactics and things involved in it. So there is a chess saying that if you find a good move, find a better one. But yeah, old-fashioned computer looking at that would just look at it, just look at everything. So I mean, for example, actually, I can't think of. I mean, so moving rook h1 g1 is complete nonsense. The same a1 b1 old-fashioned computer is going to look at that just the same as everything else. The computers don't have any emotion, but also likewise that can actually lead to computers can actually lead to good moves as well, because human beings will sometimes overlook slow moves. And sometimes a slow move is the right move to play in a situation. There's a very famous book, actually, that it's called Chernev's Logical Chess. And it was like a manual for chess players for decades. And it's actually the first example in the book. And it's black resigns. And the chess master is saying, oh, yeah, but absolutely obvious. Yeah, it has to resign here. The game is completely over. Somebody put it into an engine, and there's actually a forced draw there through just moving a piece that you wouldn't realize was relevant. So one of the famous, and it's a big kind of thing in AI as well, was when Gary Kasparov played IBM's Deep Blue. So it's kind of a foundational moment of AI, really. This is where people kind of first imagined that AI was going to take over the world. Took a while, but yeah, Gary Kasparov. It's debatable, but I think a lot of people have him as the greatest chess player ever. He was at the top of the game for 20 years. And funnily enough, he did in the early days have peers. So he won the world championship by beating a guy called Anatoly Karpov. And the first world championship match they had to be abandoned after 48 games. And 48 games where only wins were scored. And after 48 games, the score was 5-3. So only 8 of those 48 games had actually ended with a result. But yeah, it's a pivotal moment, and it comes into one of the pivotal moments of this game was because Gary Kasparov was imagining that chess computers would play, as I described, brute force, and chess computers were known for playing in a certain way. And then one of the games, the chess computer did what's known as a slow move, and Gary Kasparov was absolutely convinced that that was a human intervention. And again, it's still up in the air as to whether it was or not. But again, it doesn't change the fact that it's a pivotal moment in AI, because the first match Gary won 4-2. And lost the second match 3.5, 2.5. But yeah, the first time the computer is actually beaten, and it's what would be considered a kind of human skill chess, because it's always thought as tactics and a little bit of nuance to it. And yeah, it's proved that the computer could just brute force its way. Yeah, one of the things that kind of led to that, and that was a very powerful computer that played that game, but advances in chess computers are, skip ahead there, not got a slide for this. But yeah, chess computers started to use more subtle subtle elements. So alpha beta pruning was one thing. So that's where it's kind of doing more of a human thing, is discarding completely useless moves, so it can then look at more kind of useful moves. So it lists the moves in order of utility, and then in order to go more deeply into the good lines, it will ignore nonsensical lines. So forgive me while
I got a question.
yeah.
Do you think was Deep Blue like, what's it called? The term forgot of, oh my gosh, deterministic.
Excuse me, can you speak up, please? We can't hear.
Oh yeah, so yeah, was Deep Blue deterministic? Because in modern chess computers, they use sort of a non-deterministic thing, algorithm.
Well, I think Deep Blue was just at the beginning a kind of so it would use a kind of minimax of sorting the moves and alpha beta pruning, and yeah, I think yeah. So if you look at Stockfish and things like this these days, they are completely different. But then again, Leela, for example, is a neural network chess engine. So again, that's something that hasn't been programmed with the rules of chess. It's essentially learned the rules of chess through a neural network. So again, chess engines are kind of progressing. I mean, I think Stockfish is still the most powerful, but yeah, neural network engines, because it is kind of like I say that it is where humans and computers are alike. That if you can minimize the amount of time that you spend on pointless moves, you can then go more deeply into the moves which more have more utility to them. But yeah, I mean, Deep Blue was it was a computer program, but it was also hardware designed to play chess. And actually, the kind of story of computer chess is relatively interesting, actually, because they did used to be they were hardware, not software. And but again, actually creating the hardware for computer engines is quite complicated, because actually the moves in chess are relatively complicated. If you look at just the movement of the pieces, it can be very simple, but then you think about castling. Castling is quite a complicated thing. Castling is where you move the king 2 squares and it swaps places with the rook, but you can't do that if one of the opposition pieces is guarding that square. You can't do it if either the king or the rook has moved. Another move, which beginners always forget, is en passant. So if this pawn here was to move 2 squares here, this pawn could capture it by moving there. And so actually, superficially, chess is a simple game, but there is an awful lot of complexity to it. And if you're programming, it's difficult. If you're actually creating hardware to play it, it's yeah, another level above that. Anyway, it's right. So, fortunately, large language models do contain the word language. So we are going to have to hit upon language. ChatGPT did actually tell me that for every 5 minutes of philosophy you put into a lecture, you lose half of your audience. Claude told me it was 6 minutes. Gemini 7, and Grok AI actually gave me a naked picture of Kenneth. So green, you're interested. So I'm sure you all recognize René Magritte. Yeah. You joined us at the right time. Let's get talking about
Speaking French.
So yeah, this is Treachery of Images by René Magritte, and of course you can all understand that. Ceci n'est pas un pipe. Ceci is the French for this year, this here isn't a pipe. And the kind of philosophical meaning behind that is obviously this is a painting of a pipe. So it's not actually a pipe. So there's a difference between the words we use to describe things, and likewise the word pipe isn't a pipe either. So it's kind of making you think about what would be the word for that. But yeah, essentially,
Very meta.
yeah. What you have in your mind is a kind of conception of kind of reality. And yeah, more onto this, we come to, so probably I would say defining part of the 20th century, certainly the early 20th century intellectually, would be Bertrand Russell, the Earl Russell, and done it again, Ludwig Wittgenstein. So yeah, we've got the Earl Russell there. I'm going to shall I call it Bertie or Lord Russell? No, we'll address him with a little bit of courtesy. We're not going to talk about flying teapots or set theory. We don't want to be here all night. But yeah, so Bertrand Russell was obviously a professor at Trinity College, Cambridge, and Ludwig Wittgenstein was his student. Funnily enough, a failed engineering student in Manchester, and goes to study philosophy under Bertrand Russell at Trinity College, Cambridge. Another interesting thing, Ludwig Wittgenstein went to Linz Realschule in Linz in Austria, around about the same time as another very famous Austrian. Less said about him, the better. But yeah, so essentially kind of, I mean, so quantum theory, so you have, well, general relativity from Einstein, and then quantum theory with Schrödinger, and then obviously people like Dirac, who again, I think was Trinity Cambridge, laid the foundation really for the change in the kind of mode of thought that we kind of have. You know, they're conceptually very big ideas, and it gave birth to a lot of kind of philosophy. And yeah, so really intellectually, these are the kind of giants of the 20th century. I bet you they wouldn't accidentally be switching slides. And yeah, so Bertrand Russell was from the a movement called logical positivism. So essentially, he's wanting to directly map language to reality. So things are very logical. Things are precise. A word has a meaning, and that meaning is kind of stationary. It doesn't change. It's all very logical. Bertrand Russell was well, I mean, philosophy in those days, back in ancient Greece, philosophy kind of meant everything. And I think Bertrand Russell kind of represented that more or less in the modern world. A very talented mathematician. But yeah, this was his idea. And Wittgenstein came along, and Wittgenstein actually, in his book Tractatus, did actually claim to have solved philosophy, but I'm not entirely sure he did. I think that's still at it today. But Wittgenstein was very much of the perspective that meaning of a language is how you use it. So there's the context. And if you think about that, you know, say in your head, lecture theatre. So you're in a lecture theatre right now, but you know, some people might have gone to a university with great big lecture theatres, so that's the image that they have in their mind. Some people might have gone to college with tiny lecture theatres. Everybody's words are different for everybody from their perspective. And that's both, you know, nouns like lecture theatre, or, you know, cat. If I say cat, you might be thinking of a cat you had when you were a kid, you know, all of these things, but also, you know, verbs and things as well. And it's interesting, actually, that this kind of debate, if you were to ask people that, because we're dealing with computers, people are going to be thinking that it's Bertrand Russell's perspective that's won out in the modern world with large language models, and we see our flashing lights there at all voltages, and they're not flashing now. No, they're still flashing. But no, it's actually Wittgenstein. That's closer to the concept that we have in large language models today, because large language models are trained on real language. They, go about read websites, they read language that people have used. So it's not logical. A cat isn't just a cat. A cat is a myriad of different things to a large language model. And it is kind of an important it's an important concept for computing, and it's an important kind of concept for life as well, really, that you kind of think that you're speaking, you have an image in your head of what you're trying to say, but you have to also know that you're communicating using language, and that language can form a completely different image in somebody else's head. So how we relate that to large language models is what's known as vector databases. So I did have an example, but it doesn't work on that. That does consistently let me down. But I do actually have it on some slides. So the way large language models, they will map meanings to a numerical value or position in space. So if you have king and then you have queen, king, you move in the female direction to get to queen. So that's kind of like a three-dimensional representation of it. Unfortunately, it's not 3 dimensions. There's many more dimensions. But if you think of mapping meanings in space, you can relate words in that. So large grey would be elephant. Smaller, if you move in the smaller direction, you might get to a cat or a mouse or something. So you could kind of think of language in that way. That it and that's how it's a methodology of how what is essentially a statistical trick large language models work, because you think essentially a large language model is just predicting statistically the next most likely word. And you think, well, there's a ridiculous number of words to choose from. But if you're thinking of language in kind of a vectored space, multi-dimensional space, then you can see, you're talking about kings and queens, they're related words, monarchy, royalty, all of these words are related. So when it's using that statistical algorithm, it's moving around related terms. So that's, it's not just, it isn't just pulling things out of thin air, although sometimes it can appear that way.
Are all the links, that just occurred to me, are all the links actually, when you said smaller, larger, are they all verbs? Is that the links, or are there other dimensions beyond that? How would you link royalty to king and queen? What's the vector there? Is it?
Well, I suppose that's the kind of maybe collective or family. I mean that's one of the ways that it does get a little bit more complicated, because it is kind of multi-dimensional. So it's not. But I think it.
There's a group vector. There must be, mustn't there? Easily.
Yeah. So heading more towards group, or sort of these kind of. Because I mean, I suppose when it comes down to it, you could kind of think that it's almost kind of infinite, really. But there are.
But it depends on the input. That gives you the focus.
Yeah.
The vectors change depending on the input, which is really focusing on the vectors, isn't it?
Yeah.
It's actually it's trying to find vectors, finds the vectors, focuses on those, and that helps generate the result.
Yeah.
Okay. The cat's back.
Yeah. This is kind of wrap up. I think we're wrapping up language here, are we? Wrapping up language? I think. Yeah.
That's gone again.
Oh, here we go.
Bertrand Russell's darling.
I was looking for, this is a quote from the beginning of Star Trek. I did look for a picture of James T. Kirk, but he's just too awesome, so I had to go for the cat again. So we talk about grammar here. So actually, does anybody know what the grammatical mistake in that is?
It should be to go boldly.
Yeah, technically that's what's known as a split infinitive. So the infinitive here is the verb to go. But do you know where that comes from? Because this is English. Which one's English? No, don't need to quite get there. So we have to go, gain, alla, ire, pagano. So yeah, German, obviously French, Spanish, Latin, classical Greek. Do you see a pattern there? We get the rule that you can't split the infinitive because people in the 17th century were addicted to Latin, and you can't split the infinitive in I'm going to say any other language, but certainly Indo-European languages, there is no split infinitive in in these languages. And this is the thing with when you deal with languages, that a lot of people think that grammar is prescriptive. So there's a lot of rules. Oh, you've made a mistake there. You've written that wrong. Whereas, well, when you deal with ancient languages, there's a rule book that I don't know how many ancient Sumerians who are going to be following the rules that we write there. So, I mean, it's just I hate to, because I know people love being the grammar. Don't really want to say the German political party from the 1930s, but people kind of enjoy that. But it is actually a fact, actually, the grammar is, it's descriptive, it's not prescriptive. And that's certainly how it works with regards to large language models. Large language models will give you correct English that follows the rule because it's been trained on enough journalistic content. But essentially, grammar describes a language. It doesn't tell you how to use it. You know, you can go to the Amazon rainforest and their language is just as much grammar as ours, and nobody's ever written their rule book there. Anyway, this is personal work. I don't know what's of mine. This is completely nothing to do with the lecture, but this is actually where I would like to go back in time and have a go at a few people. All of the creatures in the world, why are they using two such similar looking birds for two such distinct sounds? Anyway, we'll move away from my my hobby horse. Oops. Almost back onto another one of my but we're skipping ahead there. So go for a bit of a timeline of where we are with modern AI. So I think we've covered a reasonable amount with general kind of artificial intelligence. You know, with things like chess, but also if you look at things like, you know, Pac-Man, they had very simple kind of AI. And, you know, the AI in computer games hasn't really changed a great deal. You played Grand Theft Auto, Vice City, the cars will drive into you the same as they do in Los Santos these days. But yeah, with regards to what we now refer to as AI, we have a kind of a distinct timeline here. So yeah, deep learning is kind of that kind of time scale around 2006, 2012. So that's neural networks have been around for a while, which is kind of computer programs that would kind of mimic the neurons in the brain. But these kind of multi-layered, where you would be able to there'd be an input and an output, and there'd be layers in between where patterns and relationships could be established. And that was starting to sort of come around that time. AlexNet was visual recognition, so that's where, so for example, recognizing handwriting is kind of an example of that. So a lot of people's kind of handwriting is different. around about 2012 is when, you know, that kind of moved on to a position where you could give a computer a picture of James T. Kirk and it'll be able to recognize it. And then, yeah, the next kind of game would be AlphaGo, which is Go is a game where I don't know how many people have seen Go, but it's counters and you kind of capture regions of the board depending on where you move the counters to. And yeah, superficially as well, you'd think a computer would be, you'd think they'd have done that before chess actually, but no, there's a lot more to it. And yeah, it's yeah, only 10 years ago that that was conquered by the computer world. So yeah, so yeah, the kind of the big thing here is this is a paper written by some people at Google. Attention is all you need. Do anything with regards to AI, you kind of really need to read that scientific paper. Scientific paper. Yeah, I'll give them that.
Did they publish Google or they?
Oh yeah, it's published. Yeah,
Stop publishing other stuff.
So
In peer reviewed, I'm pretty sure.
yeah, it was. Yeah, it's a pretty important thing. Mind you, the interesting thing about it is actually transformer architecture does underpin what we now call modern AI. It's not really the only way to go. If that hadn't existed, actually, we could still have modern AIs with similar capability, although perhaps the technology would have moved more slowly. But yeah, it's a pretty kind of critical thing, and it's kind of yeah, it's difficult to say. It's not like, because I mean, you couldn't put a square on a car and still expect it to go. And that's kind of like the same thing there. There are other architectures other than transformer architecture that could do a similar job, but that's you know, it worked, and it's kind of the one that people have. Yeah.
I just want to ask a question on this. It's interesting that Google pioneered this architecture, but they were one of the last ones to market. What do you think, like scientifically speaking, what went wrong there?
Well, I think it's the old kind of adage of kind of not really seeing the potential in things. And a lot of these big tech companies are run by business people at the end of the day. And how controversial can I be? I think people sat there at Google in 2017 were thinking, well, this doesn't steal people's information, so what good can it do for us? But you do find that as well, that I mean, unfortunately, this country's been a kind of victim of it as well. But you know, things get invented and then things get ignored. You know, jet engines and another example of that. But you need a good idea, and then you need people who can kind of think it through to the ultimate conclusion. But yeah, it is very interesting that Google missed the boat on that, really. As far as I'm aware, they're a computer company.
They're a data company.
Well, yeah, they know more about me than I do. Yeah, so one of the kind of key things of transformer architecture is I mean, it's very kind of similar to the deep learning, but it's kind of holding context in memory. So in large language models, we have what's known as a context window. The context window of modern, certainly if you take something like ChatGPT-5, you could give it the entire works of Shakespeare and it could hold that in memory. Back in those days, it wasn't quite so big, but I mean, if you go back to this kind of thing, you're talking like a sentence at a time. You know, it could process a sentence. With the transformer architecture, you're talking about retention of a large amount of context that it can kind of work with, and like I say, map into kind of space. You know, it can sort of see, and then it can work and give more informed results, as opposed to you know, going back to the sort of early days, kind of, you know, kind of statistical kind of tricks, really. But yeah, parallel processing, and I think also another advantage of the transformer architecture in itself is its scalability. So, you know, all of these GPT-1, 2, and 3, you know, they're not doing anything particularly special. They're just making it bigger. So,
Bigger in that they can do more parallel processing, or that it just
yeah, so, yeah, larger parameters, and also kind of grows with computer capabilities as well, because I think things are slowed down a little bit these days. But I mean, when you go back over these kind of years, you know, the amount of memory that was available to computers. Oh, actually, here we are actually, yeah, we're covering the move from 32 to 64 bit. So larger address space. But yeah, the next thing here is from the UK, DeepMind's protein folding. So this isn't large language models per se, but it's a similar technology. Told you we'd get back to molecular biology. I'm sorry I didn't include the cow on this one. So proteins are the sort of building blocks of reactions. So enzymes are proteins. Proteins also the cellular mechanics that move things across cell walls, structure. Very significant biologically. And obviously proteins are, obvious to me, are coded by DNA. DNA ribosomes then assemble what we have here, amino acids. Actually, one of these is an amino acid, but I noticed that's gone out of fashion since I was at university. They do label it as an amino acid now. I can't remember which one it was. I'm sure you'd be fascinated to know. But yeah,
The distinction.
it is so amino acid is this this group here, and I think this is what makes it. So actually, can we spot one that doesn't have that?
Proline. That's not the
Proline.
too.
Oh, there we go. Bingo. Yeah, amino acid, as far as I'm aware. So all of your enzymes and proteins and things are made up of these 20 constituent parts. I'm saying 20. This number off the top of my head, I remember it being 20. I'm sure they haven't grown more since I was at university. They haven't. But yeah, you can see these are kind of quite complicated. So these join themselves together in polypeptide chains. And one of the things that makes them biologically significant is that they form different shapes. So enzymes, for example, speed up reactions by folding themselves into a conspicuous shape that will fit particular molecules and then enable the reaction to take place. But you can see there's lots of moving parts there. These are very complicated when they're in a chain. You know, there's different, so double bonds there are very electron dense, so they're negatively charged, and there are positive parts, so they fold in different ways. It's very difficult to predict and to model that. Used to be done with X-ray crystallography or electron microscopes. But yeah, AlphaFold from DeepMind here in the UK was actually able to use kind of similar technology to transformers to actually model the folding of proteins, which again is kind of like quite a big step forward, really. So you're moving from theory into quite serious kind of application. So yeah, this is 2022. That's when ChatGPT first graced our graced the internet. But ChatGPT is just a UI on top of these models. One thing I don't know whether people are kind of aware of it. You never actually have a conversation with ChatGPT. When you use ChatGPT, you type what you type in, it gives you an answer, and then the next time you type something in, it hasn't remembered that. It sends the entire conversation back. So it gives the impression of a conversation, but it's not actually, it's not your friend. It might seem like it.
Is that why long conversations, it takes a long time to respond?
I would have thought it's, yeah, because I mean, the context window on these things, I mean, we're talking the works of Shakespeare,
Mhm.
could be actually. I'm just trying to think from because I write programmatically.
I find that the longer the conversation goes on, the slower it gets. So I then stop and then I start.
Yeah, I don't know whether ChatGPT is actually holding that cache on there or not. I would thought it would have to be a very, very long conversation for it to actually be the processing time. So I don't know whether it's just the transmission of, so it's sending all of the information from your computer to there as opposed to it holding it on a cache there.
It's pretty certain they have some stuff cached, and there's probably some compaction going on as well. A certain amount of tokens.
I'm betting there's also a certain amount of you're using me a lot, so I'm going to throttle down because I'm making this at the best. Yeah, I thought.
But yeah, so essentially just a kind of not particularly clever interface on top of an existing technology. But I mean, it's the thing that kind of makes things usable actually. So I mean, you can kind of laugh that it's not particularly complicated from a web programming perspective, just sending a conversation to an HPMA endpoint, but it's what makes it usable. So it is significant. And now multimodal era is where we are now. So this is a perspective where you can actually use images and voice, and it can transition between them seamlessly. So in the past, the AI would have trouble. It still doesn't produce text and images particularly well, although that's kind of improved. But you can now, in the same query, move between the domains of text and then images and voice and video. The voice chat is still
Awful.
well, as far as I'm aware, it's a separate thing. It translates the voice, so you're not actually talking to ChatGPT. But I think we are at a point where you could actually do it. But yeah.
Sorry, on that, I was just going to ask, like, what about this sort of explosion of the transformer architectures triggered this? Because like image models, for example, use the fusion architecture, which is something completely different, but they all sort of came about at a relatively similar time.
Yeah, I mean, it's a kind of a similar technology from, and it's, we're not kind of talking about sort of apples and oranges here. I think they kind of feed into the development of one another.
There was also, came in my lecture we had a little while ago, I don't remember the details, but there was a massive increase in funding for research in this area. This was, when we're seeing the early neural networks, they were getting a small percentage of the AI funding, and then in the later period when all this starts, the funding just shot up by factors of hundreds or thousands. It was just ridiculously large.
Yeah, I mean, it's
with investment comes lots of change and lots of ideas.
Yeah. So yeah, money kind of swinging about, but I mean, it does kind of have a little bit of a feel of a kind of bubble about it because when you take GPT-4, I think $110 million to train it. So yeah, I mean, they're obviously they're obviously making their money, but yeah, I think that's one of the areas that, I mean, it's kind of like a contemporary issue, really. Is it a bubble?
Yeah, they're not necessarily making that much money. They're getting a lot of investment, which is not the same thing.
Well, it's the kind of same thing as a lot of things at the beginning of the internet, really, that, people put their money in. That's all right. Yeah, I thought we'd do a little bit of a glossary. We're going to head into some demonstrations, but unfortunately, I don't really think, I mean, I could certainly give it a go. So yeah, temperature with regards to large language models. You might have seen this. Certainly, if you deal with it programmatically, you can set the temperature, and a temperature is kind of analogous to creativity. So if you're thinking of words in a vector database, where you've got sort of summer meadows here and sparkling oceans here. Low temperature, you ask it for a poem with summer meadows, just going to talk about summer meadows. Give it a high temperature, it's going to be a little bit more creative, and it's going to spread out the context it uses, and it might get all the way to the glistening sun over the over the ocean. But again, I think if you use this ChatGPT, I'm not entirely. I don't know actually whether that's something you could add to a prompt, whether you could turn the temperature up and down, but certainly if you use it programmatically. So yeah, we've discussed a context window, which is essentially how much information it can store at once, which again is it's useful for business applications. So that would be obviously you could put all of your contracts. Actually, this comes to retrieval augmented generation as well. But a context window as well is going to keep more in memory. So if you're a business and you want to query all of your contracts from the 2020s, you know, it's going to be able to do that with a bigger context window. And the context windows of these things are growing. It is tangentially related to parameters. Parameters is essentially the size of the model. So if we go back here, we can see that ChatGPT started with a measly 117 million. It'd take you 5 minutes to count to 117 million, wouldn't it? And then we have 1.5 billion. There isn't actually, they've not published since GPT-3 actually, but there was discussion of somewhere in the region of 1 trillion for GPT-4, so GPT-5, who knows? And that's the actual size of the model. So if you think of be a good analogy. So if you think of like a mixing desk, for example, so all the parameters within a large language model, it's getting trained. And so you're putting the sound, one parameter, you're putting it through one mixing desk, 2 parameters, you're putting it through 2 mixing desks. You're just getting a more kind of finer tuning. Actually, don't do that with your audio at home, because once you've gone through more than 2 mixing desks, you're getting signal attenuation. But it's a kind of example. It's fine tuning of where it is. So you're going to get instead of it just giving you the first thing that kind of comes to a mind, it can with more parameters, it can ruminate more, and it can go back over what it's given you, and you know, give you the best result. So yeah, frontier model is a word for the commercial large language models like GPT. So you've got Claude from Anthropic, Gemini from Google, Grok again. If you want your Muppet characters with less clothes, it's definitely the place I recommend. But as well as frontier models, there are open source models. Well, you can actually run large language models on your computer. The best way to do it is through a program called Llama, and they actually have. Actually, I might need to check that.
LM Studio is better.
Beg your pardon, sorry?
LM Studio is better for running local LLMs.
Oh, I've not heard of that actually.
It's a really nice GUI that wraps stuff. It has like a download list. It's really easy to use.
All right. Yeah, I use Llama because it's I'm a bit of a command prompt person. Yeah, I can't remember whether Llama is the program and Llama is Llama is the program. Llama is the model. But also there are other small LLMs, and you can actually get quite good results from them. Actually, there's a French one called Mixtral, which I find to be particularly good. I think it's about, I think it's only about sort of 7 gigabytes. And yeah, if you've got like 16 gigs on your RAM, it'll run quite well. And it's actually funny because it's related to language. I'm kind of assuming because it's French that it's been trained principally on French, but it gives pretty good English. Let's put it that way. But actually, yeah, I will touch upon that as well, actually, because language is important from that aspect. Should probably talked about it earlier. But yeah, mainly models are trained in English. So most of the results you're going to get the best result if you ask it in English. Second best, probably Spanish. I don't know what the kind of proportions of language spoken in the world.
Chinese is second, right? DeepSeek.
Actually, is an interesting example. If you ask DeepSeek for interesting photographs that have been taken in Tiananmen Square, it doesn't know what you're talking about. I don't think anything as interesting has ever happened in Tiananmen Square.
You said 1 trillion parameters, maybe ChatGPT-5. What does that look like in a hardware sense? I mean, parallel processing. You've got a rack full of servers, or are they all Linux or Unix or?
Oh, I'd imagine I would imagine there'd be Linux boxes.
Crap ton of NVIDIA GPUs.
Yeah.
I mean, how are Google or whoever coping with, or ChatGPT? How are they coping?
Excuse me, can you speak up, please?
I'm sorry. I was just wondering how do Google or whoever's running the LLM, how do they cope with expanding their hardware that quickly to cope with all the expansion and the people using it? And physically, what does that look like? Is it just another rack or another?
Yeah, I mean these kind of big server farms. You've probably seen them. They're kind of corridors full of machines. With usually a little bit of I'll come to you in a second. Usually with a bit of headway, so they'll spin up new boxes for kind of high demand. But yeah, essentially, yeah. I mean, it has. I mean, it's one of the things you're seeing these days that obviously GPUs are a scarcity these days because they're all being bought up by people who commercial LLM vendors. So yeah, it's not just
Not the sort of thing we can build in the garden shed without a wheelbarrow full of money.
well, no, it's it does cost a lot, and actually, it is an issue with regards to this technology because it is very power hungry. So it does actually have an environmental kind of cost, and you can actually, I think there are vendors out there who tell you what your carbon footprint is if you're kind of, using, getting ChatGPT to write your shopping list every day.
Okay.
But yeah, these kind of great big, but I mean, if it's kind of similar architecture to, cloud storage and things like that. So if you take sort of Amazon, there are these great big warehouses full of computers that are dotted throughout the world. So if you deploy an app on Amazon, you can deploy it locally to you or locally to your customer. And yeah, these server farms are just growing everywhere. Although I do think more processor intensive, obviously, than the average kind of website. But yeah, so I suppose they're having a battle between the LLMs and the crypto mining. So, but yeah, very, very hardware intensive. Oh yeah, sorry.
It was just on that point. So I think it was, I saw it last week. They're looking into AI infrastructure, as in like home use. So the batteries that you might have for your solar power energy and everything that happens. So you say if you're like a Tesla power battery or whatever it might be in your house, so you can be off the grid. They're now implementing GPUs into those batteries, and they're going to do a connected network of infrastructure residentially. And then that's going to be the new pull. Now, what you get off the back of it is like free energy, some other stuff. So there's going to be a trade-off and a trade back to these institutions. I can't remember exactly who is the first one to implement. It was either OpenAI or it was Google, but someone is making, I'll have to double check, but someone is already implementing these, or they put the plans forward for an AI infrastructure. So in the next possible year or so, instead of having data centers, you'll be having these boxes on the side of everyone's houses, which you're getting free energy from. So you're thinking, oh wait, I'm saving on bills, but they're also being used to train these models further. So this is how they're looking to it in the future.
Massively distributed.
Yes. Yeah, well, because they can't, it's a lot cheaper than developing data centers or AI farms or whatever it might be. If you can just implement it into people's houses, and we'll happily take it, because at the end of the day, we're saving costs on energy, especially during the cost of living crisis.
What we're effectively probably doing, because it's been talked about for a while, is using AI as an alternative to battery storage.
Yeah.
So when it's in the middle of a day and the solar panels generating loads of power and you're generating loads more power than is needed, then the AI does its thinking. And when you need the power and the power's, it's the middle of the night and whatever, then you're not getting that. So it does all the smoothing out, and it's actually a lot cheaper to just use the AI for that than it is to build batteries for that.
But they're also as their own data centers. So will be in essence their data center. They no longer need to go into Arizona and build these big infrastructures.
Yeah.
Now the home base, the residential base is their data center.
Because there is another aspect of that the smaller models are actually becoming more and more effective. So I don't really think at the moment an AI that you could run on your phone is particularly effective. But like I say,
Gemma 4 then. Gemma 4 is very powerful, something you can run on your phone.
yeah, I'll be interested to see that because, like I say, the Mixtral is, I've asked it some pretty testing questions, and to me, it's surprising what it can come up with, really, considering the size of it. 7 gigabytes seems to have an awful lot of information in there. I mean, keeps wanting to give you molecular biology. Yeah. Should have put the cat on that picture as well. At least then you'd have some relaxation looking at the cat. I think we touched upon multimodal. Token is another kind of important kind of word. When you put information into an LLM, it doesn't take whole words. It takes what's known as tokens. Again, it's an example I wanted to give you on the computer. But you're not actually going to be able to see it. But actually, it's something that you can. Oh, this computer's completely died. You can actually, if you Google OpenAI tokenizer, it'll take you to a web page, and you can actually just put in an example prompt, and you can see how it's broken down into tokens. So, for example, unusual words might be one token. But words, so if you take like a prefix is actually a good example, pre and fix, that would be 2 tokens. It breaks the words down, and when you're using things from a commercial perspective, you'll actually be charged per token as opposed to per word or anything like that. So I think it works out that generally, if you put in 100 words, you're probably going to be using something like 170, 180 tokens. But again, it's kind of quite interesting to see how it works. And again, it kind of relates to how it propagates into how it actually understands patterns and languages, and tokens are a big part of that. For small business cases, retrieval augmented generation, RAG, is pretty key. Great. I'm pretty sure it doesn't need to be those 3 particular words. I'm sure somebody came up with that to make it seem more complicated than it is. This is essentially feeding your own documents, your own information into a model, and then querying on those documents. It's a very powerful thing for small businesses, very useful for small businesses. So, for example, if you've got a customer service bot or something like that you want to give help to your customers, or I think most of these people put these bots on their websites for the opposite reason of being helpful. But imagine if you did want to be helpful, then you'd give it all of the information. And then, of course, again, if you're using your own hardware, you could train an LLM just on your information, but it probably is more useful to use a pre-trained model that can kind of understand and hopefully give reasonable answers. So agentic AI agent is again key. This is where essentially you'd be using, and I think this is a big part of where AI is going to go these days, talking that essentially AI is going to be your gateway to the internet. You're not actually going to go to websites anymore. You're not going to book your own tickets. You're just going to talk to your AI, and then agentic AI is going to take care of it. So the agentic AI is where the AI has little child processes that it sends out to book tables at restaurants or find extra information. So yeah, it's a pretty kind of key area going forward. Yeah, and model weights is essentially that's the data that it's the training data really. So just trying to think of a reasonable kind of analogy to it, but essentially model weights you could think of a model essentially as a database really, and the information that's in there has kind of different weights. So obviously, if you've got a model that's just been trained on engineering information, it's heavily weighted towards technical kind of words. So if you ask it to write a poem about summer's day, you're going to get, you know, steel and screwdrivers and kind of thing. Yeah, I did want to. This would have been magic if I could have actually got this to work, but that computer certainly wasn't having this. This is just an example of. This is some documents that I put into Chroma is a vector database. This is a two-dimensional representation. So this is just an idea of. It's actually mapped the individual documents. It's given them a score and it's positioned them in space. So this is business documents. So say this might be contracts. And then this might be, the red dots might be personnel, and then blog posts. And you can see that it's just, that's how it's kind of stored it in its mind. And yeah, that's the three-dimensional version. So we could go down the route of semi-S cobordism, which is how you would move things from higher dimensions into lower dimensions, but I think it's a little bit beyond the scope of this lecture. But essentially, this is a three-dimensional representation of similar, and you can kind of see that, you know, it's put documents in space, and
You don't know what those dimensions are.
Well, yeah, essentially, it's that's a kind of dramatic kind of simplification, really. But you can kind of imagine that maybe this is towards this direction is kind of more sort of personal information, and this is kind of legalese. So yeah, you might have your kind of blog posts about your employees and company kind of news.
But in reality, there would be many, many more dimensions.
Yeah, so
Very difficult to visualize.
it is. Yeah, I think most people. Well, actually, you see space-time just rendered. Actually, you see space-time rendered in 2 dimensions, don't you? You don't even see it in 3. So yeah, it is actually a little bit difficult to conceptualize more than 3 dimensions. So yeah, I did have some demonstrations, but unfortunately, the hardware I think is down. But how are we doing for time? Do you think?
20 past 8.
20 past. Well, that's the end of the slides. I think we'll have difficulty with doing the demonstrations, but I could do a dance.
Well, I suppose then
Did you have a question? Sorry, sir.
Yes, I'm still trying to get an overview of what's meant by AI and what it includes and what it doesn't include. And like a lot of people, you see a lot of terms being used. I'm not sure whether some of these are synonyms for there's overlaps between them or discrete. But in no particular order, most people think of large language models, of course. I also heard of natural language processing, machine learning, robotic process automation.
Yeah.
I know that actors and people in the performing arts are very concerned about voice image plagiarism. And you've just mentioned agentic AI. Now, are all those different uses of the same sort of common technology, which has had a step change up in the last 10 years because of things like transformer architecture that you mentioned? And are they all different, or?
Some of the things you mentioned kind of overlap. So the broad term for artificial intelligence would be kind of any kind of mimicking of intelligence. So not behavior that's So like a light bulb, for example, you switch that on, it's just reacting one thing. Whereas artificial intelligence would be being given some sort of information and it making a decision and reacting on that. So, for example, Pac-Man, that would be artificial intelligence. You move your little man, and actually all of those ghosts in a Pac-Man have ways that they have to respond when you move your character. So they're responding to distinct inputs in a different way. So one of the things you touched on there is machine learning. Now that used to be what we used to do in data science. Now machine learning, a simple example of machine learning would be you give blood results of 100 people, and 5 of those people have some sort of awful disease. So that's your data set, and then you put that into a computer, and these are the 100 people. This is the result. This is the blood of the people who got the terrible disease, and then it looks at that data, and then you say apply that to this 10,000. So it might not be something obvious like, a virus, but it might be a combination of different things. And it can look at the blood work and establish a pattern and then apply that pattern to a large data set. Now, machine learning isn't always that, but that's a reasonable kind of example of machine learning. So that is kind of distinct to what would be large language models like ChatGPT. It's actually similar to, I might put my molecular biology slide up again. I find it comforting. No, but I mean, similar to what I'd be doing, it seems like 100 years ago now, looking at samples. We're trying to track movement of chemicals across cell walls. I measure that by shining different frequencies of light on it, and you can see what is moving into the cells from the different frequencies of light that are absorbed or that can pass through the sample, and then applying that to larger samples to make kind of predictions about kind of mechanisms of the way things act. So that's kind of machine learning. And the other things with regard to kind of plagiarism and things, that is in the wheelhouse of modern kind of AI. So if you take models like ChatGPT are trained on information that it finds on the internet and things that people have written. And also the image generation are very much the same as well. They're trained on images. So, a penguin, it's gone out and found pictures of penguins. So when a user asks it for a picture of a penguin, it's going to use that picture of a penguin that it found on the internet. And that's where it becomes a little bit controversial, because it's, is that artist being given credit? Mm. I mean, you try playing a Beatles song on YouTube, they're going to take your money from that video. But OpenAI and a lot of these large language models seem to have been playing pretty fast and loose with other people's creative endeavor. And it is actually, an issue for our kind of creative industries, writing, graphic design. We're going to miss them when they're gone. I mean, as programmers, we're already gone, but and you don't miss me, do you? But
I think Trump was trying to get rid of copyright completely. So whatever you produce is just going to go into an LLM, and you've got no rights whatsoever.
Yeah.
And Europe's gone the other way, and we're somewhere in the middle.
We can't just decide.
We can't decide. That's the problem. Nobody in the UK can decide what to go. But I think with the Trump model, AI is going to rip riot, and if there is any benefit to be gained from it, they're going to gain. And if you don't let it rip riot and you do the sort of European model, the benefits are just not going to be there immediately, are they? Or at least somebody's going to reap the benefits first before
Yeah, I mean,
it trickles down.
but it also is, I mean, it's kind of like, hate to be jumping on the bandwagon of criticizing Donald Trump, but I mean, you know, he's not exactly one of the world's most creative people, is he? So it's a very easy decision for him to make because nobody's going to be stealing anything from him. But it does also feed into the fact that if they're, you know, if artists, musicians, writers are having their material stolen, then that market is going to dry up, and you know, things are going to stop being created because
It's interesting. It's interesting to look at the music scene because Spotify has basically, I think, destroyed a lot of creativity.
yeah,
But there are other people doing other things to other channels. I noticed a lot of music being not sold but advertised on YouTube as being out the normal stream, which is where we get it from. Spotify now is the normal stream, I think. And
yes.
there are other streaming services, but I think people are trying to break through. And I don't know about AI. I don't know whether it should be let rip or it should be controlled. I really don't know. At the moment, it's not doing me any harm. so I think it's okay, to be quite honest.
Well,
I
yeah,
do use it every day now, which is it's a big change.
well, I think it's one of those things. I mean, it's a kind of technology that you need to, you know, I think it's very easy to say the middle ground is kind of where you should be, but you know, I think you know, that probably is the easy answer. But I mean, you do have to say, I mean, you know, I wouldn't like to be a software developer in the next 5 years. I mean, I know that's not a creative art, but well, back in my day, I tried, but no, I don't think anybody's going to be paid to write that much code anymore. And yeah,
You don't think that it's more like likened to, I guess, the Industrial Revolution? Like, you know, we're not all out in the fields farming our own shit anymore. We've got tractors, we've got farmers who can do masses of stuff for us, and it would just be a shift to AI-based work in a sense. Like, I mean, there's already been an industry of like code janitors that have popped up. That instead of writing code, you're cleaning up AI vibe coded slop.
But it will get better.
The challenge is always going to be that the danger is it ends up like the autopilot problem, which is autopilots are now got so good that in those circumstances where the pilot needs to take over, they don't have the skills anymore because they don't fly enough. And the danger is we get into the same problem with programming in a lot of these other areas, where we need skilled programmers to clean up the AI slop, but we don't have them because they've been replaced by AI. So all we've got is the aging programmers who are actually going out of business. Including me, I'm not a programmer anymore. I'm definitely aging. But you know, if you're not getting the new blood in and the new people learning it, you lose that. You know, the problem is AI is going to replace junior positions first. But the senior positions, all those people started as juniors. So you need the on-ramp, you need that. And the danger is that the short-termist approach of businesses throughout, certainly Western Europe and America, they're going to get some payback over the next 10 years at the cost of not having any of those skills in 20.
There are many industries like that already.
Yeah.
So
Absolutely.
I mean,
De-skilling, isn't it?
de-skilling, yeah.
Is a huge thing, right?
Code still has to be written to train the models, so there's always going to be a need.
I was wondering about, because you're talking about the link between molecular biology and also how it links to AI. This is interesting because at the moment I've just finished studying a module on the nature of computing, and we're talking about how there was an exam on genetic algorithms and how that's been used in neural networks. I'm wondering, how does that come into molecular biology, or have I missed something?
Well, genetic algorithms are essentially you kind of give you'd write a program and you give it the kind of tools to solve it. So, I mean, for example, I did a very simple one to solve the maintenance on Countdown. So you can get it to, and at the end of the day, it is brute force. So you get all of the operands, and then it goes to all of the numbers and applies the operands and the numbers in different orders. And then it can kind of, I suppose, the next level above that is it kind of finds, in a similar way to chess. Actually, it finds the ones that are closest, sorts that, and then applies it. Yeah, I think really a lot of these things, when you talk like neural networks, for example, I mean, it is an analogy, really. The way the brain works is reasonably distinct from the way computers work. But I would say that it is a useful analogy. It's not, I mean, that's kind of the meaning of the word analogy. They're never an exact kind of facsimile. So it's just a way of thinking about things, really. And yeah, so genetic algorithms, kind of modeling natural selection, really.
I read an article about a bacteria that had been actually built, the DNA had been built by a man. So there's the bacteria there that's not natural, it's been actually built, and it is alive. The DNA was constructed. Now, the big worry, there's a book in this, if anybody's good at writing, is there somebody who uses AI to generate some DNA to create something mythical? I mean,
we're doing it already. I'm a vet, and
is there a book out there?
we're using the obviously to solve problems.
Yeah.
One of the main problems, one of the main things that we've looked at for humans is Down syndrome, and looking at the genes of Down syndrome, where now they're at a point now where they can actually identify it and get rid of that before the child is.
And the tool, there's a tool out there already, CRISPR, isn't there? Which is it's a fantastic development.
So, and that's early days. I mean, I'm not an IT person. I fell into it. I don't have a lot of tech knowledge. I'm an agricultural person. I own a tech company, but I don't know a lot about tech. I get tech guys to solve problems in agriculture. And what you were saying earlier on about, you know, and you were saying it as well, just about this new revolution. But you still need people in industry to understand what the problems are, so that engineers can fix those problems, if that makes sense. So I'd much prefer a person come up to me, a farmer, say, look, I've got a problem with one thing I've got is an AI model that monitors animals and tells you when they're going to go have foals or have calves or whatever, and it does it better than a human, right? But I needed someone to come to me and tell me that was the problem that they had. What I get a lot of IT people coming up to me with IT solutions for problems that we
don't exist.
So
IT people are really good at that.
Yeah, so it's like, come back to me with, or I'll tell them this is the problem I've got. Or when my company, I deal with a lot of different farmers, and I work, and I basically come up with technical ideas for traditional problems, you know. And that's the main thing. So I've got these tech guys coming up, and girls or whatever, and they're coming up and they're going, oh, I can fix this problem. As I say, but it's not a major problem at the moment, but you know, we'll pencil it in and see where it goes, you know. But it's amazing what's happening with genetics at the moment, and I'm really
frightening.
Well, I mean, it's everything's frightening. I mean, you know, you've got Luddites everywhere. You know, I'm sure during the you know, as you said, during the revolution, the agricultural revolution, there's a lot of frightening stuff going on for people. We're always frightened about stuff. People were frightened of the moon before they knew what it was, or the sun.
Jeez,
then we learned about it, and we're not frightened about it anymore. So, you know.
But with regards to kind of people being put out of jobs, I mean, you know, back in the kind of dark, dismal days when I used to do assembly language, it was the only way to get things done quickly. You can get AI now to generate assembly language, but underlying assembly language, you see instructions, and you know, you can see the instruction happening there. But actually, if you look at the manuals for processors these days, this is the reason why you get a distinction between AMD and Intel processors. But the instructions are the same. So, you know, the instruction set, basic x86 instruction set, exactly the same, but the way it's implemented in circuitry is different. So, for example, you can, I mean, all of the, I'm pretty sure all of the just adding numbers together are different, but some of the more complicated kind of instructions, they can take 3 cycles to complete on an Intel chip, or they could take, you know, 1 on an AMD. It's actually the way the way the chips are kind of fabricated, the actual mechanics inside the chip works differently. And, you know, that's my, I'm still useful, but actually I've not done assembly language for years, but, you know, nuances like that are something I think that are lost when, you know, skills are just distilled through, you know, Stack Overflow was the thing, and kind of in the hacking world, not that I ever used to do hacking, but there used to be a thing called script kiddies, who essentially would just kind of copy and paste code, not actually understanding the nuance of what it was. And I think, yeah, essentially, I think when you have free access to sort of easy information, and the sort of way that LLMs can kind of model things, that you kind of do lose the sort of nuance and sort of a lot of these kind of deep kind of technical skills and kind of deep understanding. So, yeah.
Guys, we're going to have to call it a day. I know there's one, our normal last question of the evening is Andrew, but if you wanted to ask another one.
I got a quite short one. What's your like educational background? How did you learn all this stuff about like, well, Bertrand Russell? I know like 2 major institutions, Oxford and Edinburgh, who teach this stuff to their undergraduates, computer science.
Yeah, well, yeah, I'm a molecular biologist by education, but as I say, I sort of saw the kind of implications of big data at the time, which kind of led to the kind of physics kind of application, and had a very good fortune to have a close friend who was a PhD in linguistics, dealing with kind of ancient languages. And again, you know, you get talking, they're fun conversations. But actually they are not. I'm sure everybody else thinks they're as boring as anything, but I've always been kind of interested in history. So, you know, when you got a background in something, you know, IT can be applied to sort of so many things. You kind of get talking, and you know, just you can see the way that you can apply your skill. I mean, data is data, really. So, you know, essentially, you know, I suppose they're very adjacent to molecular biology and physics, but, you know, you can see the sort of patterns in languages. So, for example, my friend is dealing with undeciphered scripts. So you can obviously see the patterns in that, and you can use kind of machine learning to sort of take a small sample, apply it to a bigger data set. So yeah, I mean, I think it is important, and I'd say that it's you know, whatever endeavor you have in life, it's always worthwhile looking at kind of adjacent kind of fields, see what you can teach them, see what you can learn from them. I mean, I've been very lucky in my life. I've coded alongside hackers, scientists, clinicians, artists, and yeah, I like you know, all of those different fields work in different ways, and it's very interesting to kind of see what you can learn from them. And well, yeah, be humble, and you know, because you know, different fields require different kind of application. You know, see what you can learn from them first, and then you know, you can always sort of see if you've got anything that you can apply to their particular field.
I almost do a degree in AI at Worcester. Right, last question of the evening, as always.
As always.
The guru, Andrew.
I'm a business person. I ask the right questions, probably more right observations. And I'll seize on the word context, which has been used many times, and also the figures of the amount of investment that was going in and the money being put in. So for the first half of 2025, AI accounted for 92% of the United States GDP growth. So without that, the US GDP would have only grown by 0.1%. And we've had various speakers over the 2 years I've been involved in. The limits would be the amount of electricity in the world, or various other things, but there is another limit on that, that the monopoly on lithographic etching machines is that make AI possible. They're made in the Netherlands. That's a monopoly. So there is a real world burst, especially when they're fueled by what's in it and speculation. All bubbles burst. I won't ask you for any comment or answer to my response to that, because you just be guessing as much as I. But that's, as I say, I'm a business person. I'm making wry observations that there is a real world.
Yeah,
Well, Amsterdam.
He's not a Luddite.
I used to be a polymer scientist and I understood your chemistry. Thank you.
Okay, all done. David, what can we say? Fantastic lecture, really.